Okay, welcome to the fourth problem solving session on the HOT exercises. So not the ACTA part, but let's say the pen and paper part. And this will mostly be about propositions as type paradigm, this Curry-Howard correspondence, and also some universes. And I'll just go over some of the exercises and explain how to solve them and how to go about them. So the first exercise, we're asked to define, we were given this definition of a standard finite types. So actually this is a type family, and I would like to make one small point here. Actually, if we're being careful, we should be writing a universe here, maybe the lowest universe, U0, because this is an inductively defined type family. And so in order for us to do that, in order to inductively define type families, we basically need to replace this by a universe. Otherwise, we won't be able to do things inductively because it would just correspond to having a dependent type in some context. But anyway, let's have a look at the constructors. So there's this constructor PT, which we can think of as standing for a point. Is essentially something to get us started, if you like. So for any natural number n, this is going to give us an element of fin of the successor of n. So in particular, we would have PT0, which would be in fin of 1. Actually, let me improve the tablet a little bit. I think this is okay. And we'd have PT1, which would be in fin of 2, and so on. Okay, and then there's this I, which we basically think of as like an inclusion, which takes something in fin of n and then gives you something in fin of the successor of n. And then as an exercise, we're asked to spell out the elements of fin 3. So let's try and do that. So I'm going to start off looking at the first constructor, see if I can get something in fin of 3. And of course I can, because I can consider PT 2, right? Or maybe I'll write like this, PT applied to 2, right? This is an element of fin of the successor of 2, which is 3, okay? And another way to get something would be to use the I here, this sort of think of as the inclusion. So, right, so I'm gonna want this to be fin of 3, which means over here I would need something in fin 2. So I could use, for instance, I, and then PT, and then 1, right? This will also be an element of fin 3. And I can sort of iterate this. So I can do I, and then, sorry, I should be writing a number here as well. So let's do this I2, okay. So now again, I need something in fin of n, but now I'm going to use the I like one level down. So I1, and then PT of 0. There we go. And then this will be fin, type of fin 3. And that's basically all you can get, because you can't get any lower because there's nothing in fin of 0. So there's a question, should be PT2-1 and PT10. Hang on. So PT. No. So sorry. Yeah, so the arguments here are really the only argument to PT. So PT only takes one argument. It takes a number, right? It doesn't take any further argument, but I takes 2 arguments, if you like. It takes a number here and something in fin of n. So there I'm choosing to write the first argument as a subscript, just to clutter it up a little bit. It's kind of sort of common, or actually it's explained here as well, right? It's common practice to sometimes leave these arguments explicit or to write them as subscripts when you have dependent functions like this. But basically the idea is to convince you that fin 3 has exactly 3 elements, and obviously fin 4 should have exactly 4 elements, and fin n should have exactly n elements, right? That's why they're standard finite types. Okay. So I think that's all clear. But let me just briefly go over this this induction principle here. So the idea is that if you want to define a function for every n from fin of n to some p of n x, right? So p of n is something like this, right? Then how do you do this? Well, you basically go through all of the constructors, and that's all that you need to do, right? So you would need to do something in this case here. You would need to give something for PT, because that's one of the constructors for fin. And you would need to give something for I, because that's the other constructor. But here, because you're sort of doing this inductively, you can assume that you're given something for X, like one level below, right? So it's very, very similar to having the induction principle for natural numbers, where you have to give something for 0 and you have to give something for the successor. But in the successor case, you can assume that you already know what happens one level below. And so the same principle happens here. Okay. And then there's the equations that that this f should be completely determined by g and p of n, and which essentially say that if you apply f to pt, then you get pn, and if you apply f to an I, then this sort of computes down to g of n. So this is really very similar to when you define a function by recursion on natural numbers. I hope that's all good. I'm just going to look to the chat, see if that's all okay. Okay, fantastic. Good. Then let's move on to the second problem. So this is actually a variation of how to define finite types. And again, if you want to do this inductively, really we should be writing some universe here. So I'm picking U0 because again, this is by cases, right? This is inductively defined. So I actually personally, I like this definition a little bit more. Because it's conceptually quite clear, at least in my view. So what do? You say, well, the finite type with 0 elements, that should just be the empty type. So that's this bit, there you go. And then if I want a finite type with successor of n, or otherwise known as n plus 1 elements, well, what do? I take a finite type with n elements, that this bit here, and then I just add one more. And that's all it is. Okay, so it kind of translates 0 and successor into sort of their type equivalents, right? The plus 1 and the empty type. And then we can write this notation. So I prime as this function which goes from this bit into there. So this is really the inclusion like in left, right? If you have something here, then you have something in fin of the successor by just mapping it in the left component. And pt prime is going to the right component, right? And then just selecting the unique element of the 1 point type. Okay, and that's everything that there is. And actually, if you have this I prime and this pt prime, then the induction principle is exactly as above, but you just have to prime everything. So I'm just going to write here as above, but with prime everywhere. Okay, I hope that's okay. I hope that the intuition is clear. All you need to do is you need to do for the empty case, and you need to do it for the other ones. Okay, getting all clear from the chat as well, so that's wonderful. Right. Okay, so then we're gonna try and do something with this. We're gonna play around with this a little bit. So we're gonna choose our favorite version of the finite types. Now, it doesn't really matter. I'm just gonna write them, and if you prefer, I'm gonna write them like without the prime. And if you prefer the primed ones, then just imagine that I wrote primes everywhere. It won't really make a difference. And then we're going to use splatter matching to define two different inclusions. So let me just, for emphasis, do it like this. So this is really the function. So for every n, a map from fin of n to n. And basically what we want is we want that at n, this map is going to map to the first n plus 1 numbers. Okay, that's the idea. Sorry, at the successors here. Okay, so let's try and define one, and then we'll define the other one differently, right? That was the task. So let's try and do one of them. So I'm gonna define iota first, and of course we have to do this inductively. So I'll start right like this, like with a subscript to indicate that I'm doing this argument. So iota at 0 is going to be from fin of 0 to the natural numbers. Okay, but this is empty. So I always have a map from the empty type into n, right? This is the non-dependent elimination principle of the empty type. So this thing I really don't, I mean, this can easily define this. Exactly, I don't need to do this. So I'm just gonna write a check mark here and sort of ignore that, okay? So the interesting thing happens when you want to define it at the successor, at the successor. So actually, maybe I'll do the primed ones because the solutions do the unprimed ones. So I'm going to do the primed ones. Okay, so I'm going to do it like this. So fin n successor of n to n. Okay. Well, what do we do? Let's go up a little bit just to see the definition again. So what do we do here? Well, we have two cases. Either we're getting an in left x, right, where x is in fin prime of n, or we have in right then the unique element of the 1-point type. Okay, and well, there's a couple of things we can do. One thing we could do is we could choose to map this to n plus 1. And here we're going to say, well, I have something of fin of n, so what I'm going to do is I'm going to do iota of n applied to x. Okay, and then that defines a map, and we're clearly hitting everything. You can easily prove that by clearly hitting the first n plus 1 numbers, right? Because this last thing hits n plus 1, and then by induction, the rest of the things hit everything before. Okay, does that make sense? Yes. Thank you. Sorry, so it's a good point made in the chat. This should not be n plus 1 because that's the n plus 2 number. So I'm getting my indices mixed up. So this should be n, right? Because this is off by 1 error. That is kind of happens when you do these kind of things. So I hope now it makes sense. I'm just looking at the chat to see if that's okay. Okay, wonderful, good. And then we're going to define the hat one. So iota hat to be somewhat different from this. And now again, this thing will be fine for a similar reason. And here we have same kind of typing to n. And we have again the two cases in left and in right. But this time we might send this one to 0. And then over here, we're going to do the successor of iota hat n of x. So this one, if you like, starts counting the other way around, right? So it sends the rightmost thing to 0, and then the other things sort of build back up. So they're different, but they, I mean, in many ways, they exhibit the same behavior, right? We're just counting the other way around. Okay. So I think that's all clear. So let's move on to the next problem. As you'll see, a lot of this stuff is just sort of inductive reasoning, which is fairly common when you do the way we define the natural numbers. That's sort of the only way when we allow ourselves to define things, by using the elimination principle. Of course, once you set up a bit of a theory, then you can do more complicated things more easily. So let's do another simple thing. Again, we're going to define a recursive definition of the ordering relation. So again, we should have let's make this u0 again, because we're going to do this right by recursion or inductively, if you like. So, okay, so what do we do? Well, we have to define n less than m. This has to be some sort of type. And we're basically going to have 4 cases because we're going to induct on both of the arguments. Okay, so we only need to define 0 less than m. We need to define successor of n less than 0. We need to define n so actually, let me make this a little bit clearer. So let me do these ones first. So 0 and 0, then 0 and successor of m, and then I'm choosing successor here and 0 here, and finally I'm having successor in both. I think that's a little bit clearer, perhaps. Okay, so these are the 4 cases that I have to define, and that's all there is to it. Okay. So let's do this. So here I'm going to say, well, 0 should be less than 0 because this relation should be reflexive. So I'm choosing the 1-point type here, right? We think of this as sort of true in the propositionless times paradigm. Then 0 should be less than the successor of m. That should also be true, of course. But the successor, yes, exactly. It's a good comment in the chat. So if you wanted, you could combine this a little bit. And this is what initially I started to do, but then I kind of backtracked because I thought it would be clearer to do it this way. But yes, you could be a little bit clever and just say, well, I don't need to inspect the second argument on this side, right? You could just sort of combine them. And maybe if you were doing this in a proof assistant or something, you would for, because it saves you a few lines of code maybe down the line as well. But anyway, successor of n, that should not be less than 0 because it's at least 1. So here we're going to choose the empty type. And here is, of course, sort of in a way the only interesting case, because here what we're going to do is we're just going to say, well, they're both successors, so just go down. Right? Just recursively make the call. And then in the end, you will get to one of these and that will settle things. Okay. So that's all good. Wonderful. Okay. So then there's a few exercises that basically, they're not concerned with pattern matching so much, but more about translating logical statements into type theory. Okay. So that's pretty helpful to do. So one thing that we would like to do is we would like to define is prime. Right? So we want to define a type that expresses that a number is prime. So in other words, is prime of n. So we're going to define this, and this should be a type that expresses that the thing is prime, right? It should not be like true or false or something like this. We have to write in a way a logical statement, but as a type, right? So let's do this, let's say, in English first, right? So we could say a number n is prime if the only divisor d of n, the only divisors d of n are 1 and n, right? That would be perfectly good definition. Yes, good point. Is prime if and only if this happens. Sorry, if the only divisors are this, and we want to exclude. We want to exclude the number 1 as well. So one thing we could do is we could just translate this directly into type theory. So let's try and do this. Okay, so we could say, well, first of all, we want to exclude that n is 1. So we have not n is 1, right? Remember that this is the implication into the empty type. Okay. And then we want to say for, basically we want to say for every divisor, either that divisor is 1 or it's n. Okay, so for all becomes a pi. So we're going to have for all d, in n, if d divides n, so I'm assuming that we have already coded this up, okay, but maybe it's a nice exercise to think about how to do this. If you would like to, you could look at Egbert's book. I think it's section 6, where this is discussed, maybe 7, I may be off by 1 again. But then we say, okay, well, if d divides n, then d equals 1, or, right, write a co-product here, or d equals n. And then we close this off. Okay, so this would be one way. There are many more ways of encoding this statement, depending on what you like to do, but this is just to show you one way. Okay, and you can see how I'm translating sort of the English or sort of first order logic into type theory. Is that all good? Just let me know in the chat. Okay, wonderful. So yeah, you can think of other ways, and maybe nice exercise to think of, even cleverer is maybe you can think of a nice way where you don't have to say this. You don't have to say this bit separately, right? This would be a nice thing to think about. Okay. So this is a very, very similar exercise about stating the twin prime conjecture and Goldbach's conjecture. Okay, so just to maybe refresh your memory. So what does the twin prime conjecture say? It says that, I'm just going to use some logical symbols here. It basically says that for every natural number, there is a natural number p such that p is prime, p plus 2 is prime, and p is bigger, or at least non-strictly bigger than n. Okay, so in other words, you can have arbitrarily large primes such that p plus 2 is also prime. Okay, so this would be pretty easy to translate directly, right? So let me just abbreviate this twin prime conjecture, because we just read the for all as a pi. So pi and then over natural numbers. And then this the exists we're gonna do as a sigma. Later on we'll see how to sort of refine this a bit, but for now this is perfectly adequate. Okay, and now we need to state that p is prime, but above fortunately we already defined this, so we can say is prime p. Okay, and then there's another condition, so we're going to use the Cartesian product here. So we want a pair, right? We also want that p plus, and then this is on natural numbers, p plus 2 is prime, and finally we want to say that p, or let me just swap this, because above we defined less than, right? Obviously bigger than is the symmetric version, but I'm just going to write n less than p here. Okay, so you could imagine that if you were in a proof of system, say, and you had defined all of these ingredients above, then now you would be able to state the twin prime conjecture. Proving it would be a completely different matter, of course, but at least you get stated, right? You get to make this formal impact theory. Okay. Great. So then Goldbach's conjecture is another sort of conjecture in number theory concerning prime numbers, which basically says that for every n at least 4, I think. Let me check. Yes. If n is at least 4, there exist p and q prime such that n is the sum of two primes. Okay, let's call Black's conjecture. And again, very, very similarly, we can, so I'm just gonna, let's call this G. So we're gonna have for every, right? Again, we're gonna have a pi type. And then we're gonna have this condition here that n is at least, hang on, someone is saying that looks false. What if n is 11? Right. What's going on here? Hang on. Maybe I misquoted fallback conjecture. Let me do a quick search. It's a good point. Okay. Okay. So there seems to be some variations of the phrasing, but I think the one that we were looking at needs an extra condition, namely that n is even. So thank you very much for pointing this out. So this rules out the counterexample n is 11. Okay, so this is one of the at least according to Wikipedia or something. Okay, so now we have to do this. So sorry about that, but thank you for pointing this out. We may have to fix this in the official solutions as well. So thank you for that. Right. So okay. So then I'm going to take it on faith that we are able to define something that is even, just like we did is prime. I'm sure you can come up with something that says that it's even. So we're going to have this extra condition here. So we're going to say is even n, and 4 is less than n. Right. So if both of these things are okay, then we should have a P and a Q such that is prime P times is prime Q times, and then n equals P, and then this is all natural numbers again, plus Q. Okay. That's and then I should probably close this off with another bracket because I opened one here. But yeah, it gets a little bit verbose, but you can sort of read up the statements. And with a little bit of practice, this kind of process of translating between logical statements and their sort of formal encodings in the type theory becomes quite fluent, becomes quite smooth. Right, how are we doing on time? Okay, wonderful. We're doing great on time. Okay, so for the 7th problem, we again are still looking at primes, but sort of from a different angle, if you like. So we're gonna have this assumption that we have constructed a proof of the following. So there's the name is of course a clue of what this is supposed to do, but let's look at the type first. So the type says for every natural number, there is a natural number p that is prime, and this number p is above n, right? In other words, there are infinitely many primes, right? So this infinitude of primes, that's why we have this, right? Or arbitrarily large primes, if you like. And we're also going to assume that the prime p returned by this program is the least prime above n. Okay, so let's say that our proof is a little bit clever in the sense that if you give it an n here and it gives you p back, then this is the least prime above n. Okay, And this was actually implemented in the Agda UniMath library by Egbert. So if you're keen, you can have a look. And then we want to construct from this a function which computes the nth prime. Okay, that's the idea. And we're going to do this using induction again, or recursion. So we're going to say prime of 0. Well, that should be fairly easy. We're just going to pick the first, like the 0th prime, so the first prime. So this is 2. Okay, and then the successor case is more interesting. Successor n. What should this do? Well, we're going to we basically want to find the next prime, right, that is above the nth prime number, right? So we have this thing here, prime n, right? So recursively, this gives us the nth prime number. And then let me just, so then this means that if I do inf of primes and apply it to this. So what is this? This is going to give me a pair, right? First, a number, well, actually it's going to give me a triple, a number p such that it is prime and also it is above the nth prime number. But it's also, I mean, by assumption, it gives back the least one. So that's perfect. So all we need to do is just return the first component. So we hit this with a PR1 and that's it. That's the definition. Okay, so we're exactly getting the nth plus 1 prime because of this assumption that it gives back the least. Okay, any questions about that? Okay, all good. Wonderful. Okay, so let's look at the following. So here we're starting to do maybe a little bit more logic in the sense that we look at decidability. So let's say that a type A is decidable if we have an element of A or we know that not A is the case, right? So we can make this case distinction. So then the question is, do we expect that for every natural number, it is decidable whether n is a prime, right? That's just sort of unwrapping this back into English, if you like. And so why or why not? Okay, and I claim that it is decidable. And the reason is that if I give you a natural number n, you can easily give me an algorithm that decides whether this is prime, right? So all that you would need to do, I mean, they're clever algorithms, but you could do a sort of naive algorithm where you just check, you just run through the numbers below n, you check if it's a divisor of n, and if it is, then you check if it's, if it's not equal to 1 and not equal to n, and then if you hit such a thing, then it must be prime. And if you exhausted all of the numbers below, then you know the number must be prime because you never found a non-trivial divisor. Okay, so that is just sort of a sketch of why this would be decidable. Just implementing this algorithm. Okay, and if you have a little bit of time on your hands, you can actually try and implement this in a proof assistant. Okay, so let me just write something in the box here. So yes, because we can check if n is prime through an algorithm. right? Just like some finitary procedure that's going to return whether it's prime or not. Okay. That's the gist of it. And I think this algorithm is also implemented at the same place in the Unimath library. So if you want to have a look, you can check. Okay, good. Now we have only 2 problems left. One more regarding primes, and then one final one using natural numbers and some equalities again. Okay. So let's do the primes one first. So suppose that we had done this, right? So we completely formally give a proof that for every n, it is decidable whether n is prime. And using this, we would like to construct a function prime counting, which computes the number of primes less than or equal to its input. Okay, so it's kind of interesting that you can do that just from the decidability thing. And I think at this point it will come in as no surprise that we're going to do this recursively again. So we've been doing this all the time. So prime counting, well, of course, as usual, the 0 case is easy because there are exactly 0 primes less than or equal 0. So that's fine. And then let's look at the successor of n. Okay, so the basic idea is as follows. We want to compute the number of primes less than or equal n plus 1. And by recursion, we can compute the number of primes less than or equal n, right? We can just call the function on the argument n. So really all that we need to do is we just need to check the number n plus 1, because if it's not prime, then this number will be like the number of primes less than or equal n plus 1 is exactly the same as the number of primes less than or equal n. And if the number n plus 1 is prime, then all we need to do is add 1 to this number. Okay, that's basically the gist of it. We just decide is n plus 1 prime. If it is, then we add 1 to what we previously had, and otherwise we keep the result as is. So that's the idea. And then how do you sort of implement this using the decidability? Right, that's the interesting bit. So what I'm going to do is the following. We can sort of write a helper function, if you like. So we could have h, which goes like this. So is decidable is prime successor. We count the parentheses here, n, and then goes to n. Okay, so what's h going to do? H is going to exhibit this behavior that I basically just described. So h, so okay, now remember that is decidable is defined to be this coproduct here, right? So either the type or not the type, which means we have like in a left case and an in right case. Okay. And so what we're going to do here is we're going to do in left, in which case this number will be prime, but we can just sort of ignore the argument. So I don't know, let's call it x. So here we're going to say, well, if the number is prime, then we're going to take the successor. We're going to add 1 to prime counting n. Okay, and if it's not prime, then I'm just going to call the original result prime counting n. And then finally, the prime counting function will be h of is decidable is prime, and then successor of n, because that is exactly what this function h took as an argument, right? So h is like a helper function that just case splits for us, right? That's all that's happening here. Does that make sense? Yeah, so someone's making a comment about we're using a where clause. Yeah, I mean, that's exactly how I would sort of do this. If I were doing this in Agda, I would write a where clause. You could also do it somewhat differently. You could, set up this function sort of more globally, take any n or something like this. And but yeah, I think it's helpful to think of it this way, absolutely. But that's the idea, right? And so it's kind of nice that all you need is that you need to decide whether you need to know whether that is decidable, but that's really all there is to it. So it's kind of cool that you can do all of that just using that. Okay, wonderful. Let me just add time again. I think we're doing well. Should have plenty of time to cover the final question, which is asking us to show that k is an injective, like adding the number k on natural numbers is an injective function which respects equality, right? So in other words, this direction, the left to right direction, this one, this is saying that it respects equality, right? Because if m is equal to n, then adding k to m should be the same thing as adding k to n, right? It shouldn't give you a completely different result because m and n are the same thing. And then the other direction, this one, is giving you injectivity, right? It's saying that if you add k to a number m and you add k to a number n and the result is equal, then their inputs m and n have to be equal as well. And so we're asked to prove this. So obviously we're going to have to find. So this really is it's just a conjunction of functions going in both directions. Okay, so we have to find functions in both directions. So let's do this direction first, because as you can probably imagine, that's the easier one. Because all you need to do is respect the equality. So what can you do? Well, remember AP. So what did AP do, right? So in general, if you have a function f from x to y, then AP of f would be, and then for like this would give you, if x equals x prime, then f of x equals f of x prime for every x and x prime in x. Okay, that's what AP was doing. We defined this using like the induction principle. So you sort of send REFL to REFL here. I don't know the exact lecture number that this was covered in, but it was covered at some point. So actually this left to right direction, it doesn't really matter what the functions, you will always have this sort of behavior. So all we need to do is we need to do AP, and then we need to specify the function that does this, but the function is just lambda x plus natural numbers k. Okay, so this function here, this one, is just giving you the left to right direction. Is that all good? Wonderful. Okay, then for the final proof, let's make a little bit of space. Here we go. So this one is maybe a bit trickier, but not too bad. So what we're going to do is M and N can be like, will be arbitrary, but I mean, really, okay, so this is at M and N in N, right? But we're going to do induction on K. Okay, so by induction on K on the thing that we're adding. So let's do the inductive proof. So start off when K is equal to 0. And then we assume to, right, so there's a question where the first part would be Mn and at K. Yeah, I mean, the K is already mentioned here. So it is at K, but I mean, the thing is, in this function, the arguments M and N don't appear at all. So I just wanted to clarify that. But the K does appear here. So I think that kind of, that's kind of okay. Makes sense? Cool, thank you. Good question. Right, so going back to this inductive proof, we assume we're doing the case where K equals 0, and we get to assume the right-hand side. So writing out the right-hand side says that M plus 0 is equal to N plus 0, and I'm just going to assume that I'm going to name the witness of this P. Okay, and we have to show that M is M equal to N. And it turns out this is relatively easy because M is definitionally equal to M plus 0. You can look this up again in the lecture note, but this is just how we define this, one of the defining clauses of addition. So I can always use this without any problem. And then this is by assumption equal to P. So this is N plus N0. But then I'm using the same trick that this is definitionally equal to N. And so here we go, right? So and now you can actually, so it shows that because the definitional equalities kind of, they sort of compute the P is actually also a proof that M equals N, okay? Or you could concatenate it if you wanted to. So you could do something like, so the new proof would be REFL and then P and then another REFL. Maybe this was named concat in one of the lectures, right? But I'm just using this concatenation of paths infix symbol, okay? Right, then we're going to have the successor case. So K is, let's say, the successor of L. And in this case, we get to assume, and again, I'm going to call it P. We get to assume that we have M plus successor of L equal to N, and then the successor L. And we have to prove that M is equal to N. Okay, there we go. So again, I'm going to start off. Well, let's do some rewriting on P actually. So we have M plus N successor of L. This by P is equal to N plus the successor of L. Okay, and again, if you look at the defining clauses, and if we're adding the successor of something, this is defined to be the successor of adding like one less, so adding L in this case, right? So that's what's happening on the left-hand side. And then of course, similarly on the right-hand side, I'm just going to continue here. So this will be the successor of N plus L, okay? So I have these things so far, and of course, because I'm doing the successor case here, I should also have an induction hypothesis. So let me just do it in green for emphasis. So what does the induction hypothesis give me? Well, it tells me that it gives me a function, if you like, that if m is equal to n, sorry, if m plus l is equal to n plus l, then just write some parentheses here, then m equals n. Okay, great. So that's sort of all of the data that we have at the moment. And in the end, we want to get to m equals n. Okay, so we want to get to this part, which means essentially by induction hypothesis, it suffices to prove this. Right, so formally speaking, we could apply this function, and now all we need to, we could apply the induction hypothesis, and all we need to do is get this, right? So this is, in a way, our new goal, if you like. Right, this is sufficient. Okay, let me just make a new page. Hang on, change the background. Plain, sorry. Okay, but yeah, so now the idea is going to be that, so let me just write this down for clear. So we want m plus l equals m plus l, and we have by this reasoning here, all of this bit, we have that the successor of m plus l is successor of n plus l. And now you can play this trick that like the successor is injective. Now use so it's injective. Do that. What? Wait. One. Okay. I have a little bit of time, so maybe I can say a little bit about how you would, because then this kind of leaves this additional thing that you have to take on faith here, namely that the successor is injected, right? So how would you do this? Yes, exactly. So there's an excellent comment in the chat, which is exactly where I was going to go next. So let me elaborate on this comment and do what I was going to do. So to show this bit, to show this bit, sorry, sometimes the tablet isn't exactly doing what I want. What we're going to do is you define pred from n to n. You define this recursively. So the predecessor of 0 is just 0 because the natural numbers have this least element. And then the predecessor of suc of n will be n. And so now if you have, sort of going back to this original proof, if you have successor of, I don't know, let's do a plus b. No, sorry, if you have successor of n equals successor of m, then you can do this thing where you do AP of pred, right? I apply pred on both sides. So then this is pred of suc n equals pred of suc m. But then this thing is by definition n, and this one is by definition m. So then you get this inductivity of the successor just by doing AP pred. Okay. That's, I think, by far the smoothest proof of the inductivity of the successor. So that's something you would then use to prove this. Yes, you can see it takes a few steps, to actually prove this. This is probably the longest proof that we've done, but I also went into the details quite a bit. Okay, that covers the exercise sheet, and we have a few minutes left. So are there any questions at this point? Not really. Okay, good. Yeah, so maybe just to quickly recap some of the sheet. So one thing to take away from this is that one sort of practical advantage or practical use of universes is that they allow us to inductively define these type families, but also inductively define relations like this, right? So this less than relation is inductively defined, and for this you need universes. So that's really quite sort of a very basic feature, but very, very useful to have. And then a lot of the other stuff sort of involves pattern matching on natural numbers and doing your proofs that way. And we've kind of moved away a little bit from writing all of this, super formally using eliminators and so on, kind of trusting that by now you're comfortable with the fact that we can translate this sort of like case split definitions or pattern match functions, let's say, into formal proofs with eliminators. And then there's a bit of encoding as well, of like logical statements into type theory, which I guess is not, I mean, it takes a little bit of time to get used to at start, but once you get going, it becomes a sort of second nature quite quickly. Right, then we looked a little bit about citability, and then finally we had this proof involving the APs and more inductions and so on. Okay, so I'm going to stop the recording here if there are no questions, and pause the share, and thank you for your excellent comments.